Our next speaker is Chris Polly from Fermilab, and his title is Who Ordered That? Which certainly some little birdie tells me that must have something to do with muon. So Chris, why don't you take it away? You're muted, I believe. You'll have to unmute. There you go.
Okay. Okay, so first I said thank you, Priska. Good to see you. So unfortunately, we all couldn't meet in person this year, but at least APS has managed to allow us to conduct this virtual meeting, so that's great. It's been going really well from the sessions I've been in so far. I was asked to talk to you a little bit about the Muon program we've been developing at Fermilab. And so I thought I'd start by talking a little bit about the history of why these precision experiments can be so interesting, starting with magnetic moments themselves. So of course, they've been an invaluable tool for a very long time in probing basic physics. And if you go back to your undergraduate textbooks, you can determine for a system of classically charged particles, you can calculate the magnetic moment simply as a sum over the charge to mass ratios of the constituent particles times their independent angular momenta. With a magnetic moment, you can create a torque in a magnetic field, you can define a potential energy, and then you can move that into the world of spin, where you have fundamental particles with spin, and define the magnetic moment as being proportional to the spinner, some fundamental constants, and this factor we pull out front called the Landé G factor. You'll hear a lot of references to the G factor throughout this talk. You can essentially think of it as a proportionality constant describing the strength of the magnetic moment experienced by a particle in a magnetic field. You can determine the G factor by measuring the Larmor precession frequency, watching how the particle, a fundamental particle, precesses around the magnetic field, very similar to a gyroscope in a gravitational field, as you see in the animated figure on the right. So for a spin 1/2 point particle, in a classical theory, you would expect the Landé G factor to come out to be 1. However, with Stern-Gerlach and atomic spectroscopy experiments in the 1920s, it became quickly apparent, at least for the electron, that the G factor was in fact 2. So the electron, or a muon for that matter, precesses twice as fast as you would expect and has a magnetic moment that's double the strength. The solution of this G problem appeared in 1926 when a full relativistic treatment was done by Thomas. It was then incorporated in Dirac's famous equation by 1928. So in general, for an elementary spin 1/2 point particle, the expectation in Dirac's theory is that G would be identically equal to 2. That was a very successful theory for a while, but then experimentalists started to make even more precise measurements, and let me first say, as a quick aside, the success of this Dirac theory got experimentalists fairly excited about making measurements for the G factor of the proton, because of course at the time it was also known that the proton behaved as though it was a spin 1/2 particle. In fact, people were so enamored with the theory that it resulted in this somewhat famous statement to the experimentalist from Pauli, "Don't you know the Dirac theory? It's obvious that you should find G sub p equal to 2. Like good experimentalists, they did the experiment anyway, and they were surprised to find G sub p was equal to 5.6. So in some sense, you can think of this as the first anomalous magnetic moment. Of course, that same year, once you know G sub p, you can then infer for the deuteron what the Landé G factor should be for the neutron, and it turns out to be a negative 3.8. So you can imagine how confusing that must have been to even understand how does a neutral particle develop a magnetic moment in this classical sense where it's generally a sum over charge to mass ratios times angular momentum. Of course, we now know it took 30 years to really come up with a model, but we now know, of course, that the proton and the neutron are not fundamental point particles. They're made of a lot of stuff, and this was the first harbinger that they were made of new things. So going into the next chapter of the story, which I like to call Proof That Nature Abhors a Vacuum, things were in pretty good shape until 1948, when gains in the precision measurements for the electron G resulted in a value that you see below, where for the first couple of decimal places, it looks like the Dirac theory is all that's there, but by the time you get into the third decimal place, you see that you start to deviate from the prediction of 2. In fact, you deviate by about 0.1%. And that's because in reality, particles in the universe are never really alone. We now know virtual particles can continually fluctuate in and out of the vacuum. In fact, the more massive the particle, the higher the probability is that these friends will appear unexpectedly from the vacuum through virtual loops. These alter the bare interaction between muons or electrons and change the G factor. And the extent to which G differs fractionally from 2 is what we call the anomalous magnetic moment. This puts us in kind of a unique situation. We're one of the only experiments that goes out to measure something that's actually called an anomalous magnetic moment. So if you find a discrepancy between experiment and theory, you're constantly stuck with the confusion of saying you have an anomaly in the anomaly. Therefore, we usually just say discrepancy. So it didn't take Schwinger long to figure out what was going on. He was working at the time on the calculation of this first order electron self interaction, the Schwinger term. And you can see the impressive agreement out to 4 or 5 decimal places. It became clear that he was on the right track, and QED was discovered through this continued push and precision. Of course, now the QED calculation is out to 5 loops. It requires a grueling calculation over 12,672 diagrams. And you can see the current values below for the electron G factor experimentally. Oh, sorry, that should say GE on both of those, my mistake. But that's a comparison between the experiment and the standard model, which now shows a somewhat interesting 2.4 sigma tension after the experimental value has been updated for the more recent evaluation of the fine structure constant. I would encourage you to go see Jerry Gabrielsi's talk in session G3 for the details of this beautiful measurement. Okay, so moving on to the muon. Of course, muons were discovered in the 1930s. Quite surprisingly, for people who might not know, they were discovered at the peak of Pikes Peak in a cloud chamber constructed by Anderson and Nettermeyer. If you can't see the particle in there, this one's kind of a surprising event because it actually originates in the chamber itself instead of the target, and you can see the track there. So it's amazing, you find an event like this where you realize you suddenly have a new charge to mass ratio, and it becomes clear there's a new particle in the universe, and thus the famous statement from Robbie of who ordered that. It didn't take long for people to start exploring the properties of the muon. You can see in this paper from 1957 by Garman, Letterman, and Weinreich, the first measurement of that proved that the muons decay is parity violating. At the same time they were discovering this amazing fact, they also were able to measure the G factor of the muon for the first time and found it to be consistent with the spin 1/2 point particle. Also very early on, charged lepton flavor violation measurements began. Of course, at the time when it was discovered, they didn't know that there were these families or these families of leptons, but nevertheless, experiments to look for processes like Mu-e gamma, or muons converting into 3 electrons, or muons converting in the field of the nucleus began almost immediately. The original motivation was quite different than the reasons we do it today. Originally, the initial question was really trying to understand, is the muon just a heavy, excited version of an electron of some sort? Will it decay back down into an electron? That evolved into testing the 2 neutrino hypothesis to really determine whether or not there were 2 distinct flavors of neutrinos in the world. And you can see how that's evolved over the many years in between, such that now going into the future, experiments like Mu2e at Fermilab and Comet at JPark are targeting sensitivities in the 10 to the minus 16 to 10 to the minus 17 branching ratios. So that brings us up to today. Muons are still extremely good probes in the search for new physics. That's because they can be made quite easily. They tend to not get ensnared by the strong force, at least not as much as other particles. They have a relatively long lifetime at 2.2 microseconds at rest, and they're relatively heavy. Relative to the electron squared, the square of their mass is of 40,000, and the sensitivity to new physics often scales as that square. So that allows them to be used to study some of our most compelling questions. Questions like, why is the standard model Higgs so light? What is the nature of the dark matter that permeates the universe? And more generally, are there any other sources of beyond standard model physics out there? Furthermore, the muon G-2 and the charged lepton flavor violating measurements are extremely complementary to direct searches at the LHC and to each other. And you can see some diagrams below of how new physics can enter both G-2 and charged lepton flavor violation. Muon G-2 is primarily sensitive to new physics through these loops, through the virtual particles that appear, and the standard model calculation is now known to about 420 parts per billion, compared to the 540 parts per billion that was the measurement that was made at Brookhaven between 1999 and 2001. That leads to an intriguing 3.3 sigma discrepancy between experiment and theory that has really stood the test of time in the 20 years that have gone between when Brookhaven made its measurement and the theory has continued to improve till today. I would encourage you to see Aida El-Qadra's talk in session D4. She gave a more complete discussion of the standard model calculation, which I won't have time to go into today. In addition to being sensitive to loops, muon conversion is also sensitive to contact terms. So you can see in this treatment by Andrea de Govia how you can define a parameter or kappa that essentially tells you how much of the new physics comes in through loops versus contact terms. And there's regimes where the loop dominant terms can come from SUSY or heavy neutrinos, or where contact terms might arise from compositeness, Z primes, and leptoquarks. You can see how that sensitivity scales for various types of experiments on the left as you change that parameter kappa. So moving on to the Fermilab Muon program. This is the vision for what a few people started looking at doing back in around 2012. It actually started a few years prior to that. But the idea was that it was apparent that the Tevatron was going to be shutting down soon, and suddenly a whole, back in 2009, and a whole host of equipment would become available for the first time for constructing new experiments. So this idea emerged to build a Muon Campus at Fermilab that would allow us to make the world's most powerful customized beams needed for experiments like next generation Muon G-2 or next generation Muon conversion experiments like Mu2e. To do that, quite a bit of the accelerator complex had to be reconfigured. We converted the P-bar source into a custom Muon source for the G-2 experiment, and also to provide beam for the Mu2e experiment. We extended the tunnel infrastructure and 2 new beam lines to go out to 2 new experimental halls. You can see G-2 in the background, Mu2e in the foreground in this picture. There's the 2 experiments. And then we recycled a lot of the Tevatron refrigerator equipment in order to make a centralized cryogenic facility that would allow cryogens to flow to all the superconducting magnets needed for these experiments and potentially future experiments. So this is what it looks like in around October 2016 after the civil construction had been completed for both G-2 and Mu2e and for the various components of the Muon Campus. You can see G-2 in the background with the orange fin, the cryo plant here with the tank sticking up and the orange tubes coming out, and Mu2e over here on the foreground. Just blowing that up so you can get a better picture. Those are the 2 experimental halls. So you can see it's quite a vibrant program happening at Fermilab right now. The way the beam is established, we start with 8 GeV protons that are delivered from the booster into the recycler ring at Fermilab. We split those bunches from the booster into 4 sub-bunches, each with about 1e12 protons. They're circulated around, extracted 1 sub-bunch at a time onto a target station formerly used, and it's the same target station that was formerly used for anti-proton production in the Tevatron era. But in this case, for the G-2 experiment, we collect the pions that then decay to muons as they travel down the first beam line and are injected into the delivery ring. This delivery ring is the source that used to be used to accumulate anti-protons for the Tevatron program. We reconfigured it, and it's now for the G-2 experiment, a pre-injection ring where the muons and the remaining pions can circulate 3 or 4 times, long enough that the protons separate by time of flight, and we can inject a very clean muon beam into the G-2 storage ring. For the Mu2e beam, it's very similar up to the extraction from the recycler, but then the 8 GeV protons, instead of striking the target, they instead bypass it. They're injected directly into this delivery ring where they circulate, and they're slow spilled 1 small little bit at a time out into the Mu2e apparatus, where you can see their solenoids here. So that, as you can see, this creates a very versatile reconfiguration of the Tevatron equipment that allows us to meet the unique needs of both experiments. So moving on to the Mu2e experiment. Mu2e is searching for muons that spontaneously convert to electrons in the field of a nucleus. The goal of the experiment is really to reach a single event sensitivity to branching ratios as low as 3 × 10⁻17. That's roughly a 4 order of magnitude improvement over the last experiment, which was syndrome 2. And one of the nice things about Mu2e is any signal is unambiguously due to new physics. That's because we know the only standard model contributions that come in by the virtue of neutrino oscillations, and the probability of having a neutrino oscillate is very low. The branching ratio you would predict is smaller than the 10⁻50 level. Here you can see a picture of their apparatus. It starts with a production solenoid where the protons are brought in and strike a target. Pions are captured in the production solenoid, and as they decay to muons, they're transported down a transport solenoid into a muon stopping target. The stopping target is aluminum. They wait and look for a conversion, and then they use tracking detectors and calorimeters to resolve the potential decay electrons from the stopping target. So the signal that they're looking for is a monoenergetic 104.97 MeV conversion electron. They build their straw tracker in a way that it's optimized for these energies. You can see it's this interesting arrangement where there's no material in the middle, so the smaller energy electrons essentially leave no signal in the tracker, and it's only the larger energy conversion electrons that leave tracks through the planes that can then be reconstructed. The primary backgrounds they have to worry about are beam-related backgrounds that can come from times when the beam is first injected, cosmic ray backgrounds that can produce an electron in the same energy range, and then decaying orbits that can be smeared out to the point that an electron, they start to approach this 104.97 MeV endpoint. So the key to their experiment is really controlling the backgrounds. Beam-related backgrounds are controlled by delaying the measurement window. You can see how a typical time structure looks for them, where they bring in their proton pulse, they have a prompt background, and then they have a signal that stretches into a window here that they define as the live window. And the live window is where they search for their events, thus avoiding beam-related backgrounds. Decay in orbit really requires low mass detectors with an extremely high resolution. You can see the theory prediction for how those decay in orbits look after they've been modified by nuclear effects. And you can see a blown up version of that plot on the right here that's included all of the acceptance and detector reconstruction effects. So you can see it's really critical for them to have a very low mass detector with a very high resolution. Cosmic rays have to be vetoed. And there's quite an extensive 4-layer veto that's being constructed for the experiment. And I would encourage you to take a look at Ben Barton's talk in the Q13 parallel session, where he went into the details of this cosmic ray veto. As for the physics reach, you can see the predicted background events in the table on the left. This is with their latest and greatest Monte Carlos. And you can see the background prediction for 3 years of running, which is equivalent to having 3.6 × 10⁻20 protons delivered to their delivered to their production target, is about 0.41 events. With 0.41 background events, and that length of running, you expect 7.5 signal events, and that's if you have a branching ratio of 2 × 10⁻16. That gives you 5 sigma discovery potential for that branching ratio, and gives the single event sensitivity for a branching ratio of 3 × 10⁻17. In terms of the schedule, their civil construction is complete, and the experimental apparatus is all under construction right now, with the time to complete being driven by the solenoid schedule and the time it takes to make their massive solenoids that are the production, transport, and target solenoids. They expect to start.
10-minute warning. Thanks.
Thanks. So they expect to start installation commissioning in 2021, with data taking to start in 2023. And you can see some pictures here of all the various pieces that are under construction. Moving on to the Muon G-2 experiment. The goal of the G-2 experiment is to reduce the experimental error on a mu by a factor of 4 and resolve this long-standing BNL G-2 discrepancy. For that, the experiment requires 20 times the Brookhaven statistics and better control of some of the key systematics. So if this discrepancy that was measured in Brookhaven persists, the anomaly without any improvement in the theory would grow to greater than 5 sigma result. With anticipated improvements in the theory going into the future, that difference could be, in fact, be as large as 7 sigma, again, assuming the central values remain the same. To understand the key to the G-2 experiment, I have to tell you a little bit about some of the experimental principles. We start by injecting polarized muons into the storage ring that are obtained naturally through the parity violation in pion decay. They come through in the back of the picture here through these orange beamline magnets and are injected into the muon G-2 storage ring you see here in blue. Muons circulate around the ring at the cyclotron precession frequency, given to first order by this equation. The Larmor precession frequency of the muon spin, by comparison, is given by this equation. And so it's interesting, if the cyclotron frequency and the Larmor precession frequency are equal, then essentially the spin vector and the momentum vector are forever locked together as muons go orbiting around the G-2 storage ring. When you take the difference of these two simple expressions, you see something very interesting happens. You find out to first order, the difference frequency, which we call omega A, is proportional directly to the anomalous magnetic moment of the muon, so G-2/2, times the magnetic field that the muons are experienced with some other fundamental constants like E/mc. So that means if the anomalous magnetic moment is not 0, then the muon spin no longer stays in lockstep with the momentum, and it starts to precess relative to the momentum vector. And that's really the key principle behind the experiment. So in order to complete the experiment, we have to measure two quantities at high precision. This omega A precession frequency, this difference between the Larmor and the cyclotron precession frequencies, and the magnetic field that the muons are in. Just a aside on how we're able to see the spin direction of the muons. Parity violation muon decay results in the highest energy decay positrons being emitted in the direction of the muon spin. At the end of the day, what that means is that the energy spectrum modulates at the omega frequency. As the muon spin is aligned with the momentum versus anti-aligned with the momentum, the energy spectrum oscillates up and down at the omega A frequency. And if you draw a cut and plot that versus time, you get the infamous G-2 wiggle plot like the one shown here, which is simply the exponential decay of the muons modulated by this precession frequency. So the experiment sees A mu directly, which is an 800 times improvement in the sensitivity for free compared to an experiment at rest that would measure G. So if you've ever wondered why do we go through all the trouble of building this giant 14-meter diameter storage ring to do the experiment, now you know the reason why. So as I mentioned before, it's not just about measuring A mu, we also need to know the magnetic field. So through a change of variables, you can rewrite the equation that I showed you before in terms of the free proton precession frequency omega p and some other fundamental constants. You can see those fundamental constants we're able to take from the co-data. They're all determined much more precisely than we need, since our overall goal for the experiment is 140 part per billion precision on the measurement of A mu. So at the end of the day, what we need to do is measure the omega A frequency, map the magnetic field very precisely, and convolve it with the distribution of muons in the storage ring that are sampling that magnetic field. So unlike the Mu2e experiment, where it comes down to really understanding and controlling your backgrounds, this is really more of an AMO type experiment where we really need to understand all the systematic errors on omega A and omega P. As I mentioned, our total error budget is 140 parts per billion. 100 part per billion of that is statistical, and we define an error budget for omega A and omega P each individually to be a total of 70 parts per billion. You can see in these tables, I won't go through them in detail, but you can see in these tables all the dominant sources of error that were in the Brookhaven experiment in the column on the left, and the steps that were taken to improve the experimental apparatus at Fermilab to attain the goals you see in the right-hand columns. And so this is really where the bulk of the analysis time is spent, understanding each of these systematics and convincing ourselves that we understand them at an adequate level. So just to finish by telling you the current status of the G-2 experiment, run 3 just ended. You can see the collection of our decay positrons on the right in units of the number of times BNL statistics we've sent to tape. We now have a total of about 6.5 Brookhavens that have been written to tape, and we expect roughly about 5 of those to be physics production quality after data quality cuts and systematic runs are removed. Analysis of the run 1 data is nearing completion. Right now it's still blind. I can tell you though, it has a statistical error that'll be in the 400 to 450 ppb range, depending on exactly how early we start those fits to the famous wiggle plot. And you can compare that to the Brookhaven precision of about 540 ppb. The vast majority of the systematic errors in the prior tables have all been assessed and achieved and are meeting their goals. There have been a few errors that have been more challenging, particularly due to some inferior run conditions that were present only in our first run 1 data. I'd encourage you to take a look at some of the parallel talks in the Q12 and Q13 sessions where these systematics were discussed in some detail, or feel free to ask me in the question and answer session. Run 2 data is in the middle of reprocessing, and run 3 will be starting soon. We're anticipating the final publication of run 1, possibly even more data within a year. So in conclusion, precision measurements of magnetic moments in charged lepton flavored violation have had a long history of discovery. There's a new exciting era that has dawned at Fermilab with the construction of the Muon Campus. Muon G-2 is on the verge of publishing first results. The run 1 result will be slightly better than the BNL result, and the data has already been written to tape from subsequent runs that will reduce that error by another factor of 2. So overall, we're on track for the ultimate 4-fold reduction in the experimental error that we expect by the end of the experiment. With Mu2e coming online in 2023, there should be an exciting flow of results from the Fermilab Muon program for many years to come. So thank you, and I'll be happy to answer any questions you have.
Okay, so thank you very much. I have put in a thanks that you can like in the chat window. Thanks for your talk. And I have a few questions here. Let me read them off to you. So you'll have to go back to the slide QED out to 5 loops. And the question is, the difference shows up in the 5th decimal. This is from James Sheeran.
Oh, sorry, that's a typo. The difference shows up in the 3rd to last decimal place here. My mistake.
Yeah, so a lot more.
This used to be comparing G-mu. This used to compare G-mu and GE. That's where E and mu start to diverge. My apology for the confusion.
Okay, we have another question from Miguel Castro Colon. What does it take to, sorry, that means that you were very much in time, Chris. What does it take to achieve 4 orders of magnitude improvement in Mu2e, both funding and time-wise?
Okay, that's a good question. So 4 orders of magnitude, the time part is easy. The expectation is that that when the experiment is operating, they'll be able to collect 1.2 times 10 to the 20 protons on target per year. So that takes about 3 years. And financially, the overall, I assume you're asking about the overall operational cost for the complex. That number I couldn't tell you. I'm not familiar with their operating costs.